Welcome back. This is the solution to the fifth and final problem on the optimization worksheet. Find the point on the curve y equals root x that's closest to the point 3, 0. So I have this started off with the distance formula between 2 points. This is a formula that you may have seen a long time ago and potentially forgot, so I just wanted to remind you of it. It's possible that you could see problems that have the same setup where it's like the distance between a function and a point. So if you did forget this formula, just refresh your memory now, and it'll serve you well later. So this distance formula here is really just the Pythagorean theorem, right? So you have your 2 points and you make a little triangle out of them. So one side is the difference in the x's, one side is the difference in the y's, and this formula is the distance of the hypotenuse, which is the straight line distance. All right, so let's get a working visual of this graph and this point and how they relate to each other. 1, 2, 3, 4, 1, 2, 3. All right, so y equals the square root of x starts at 0, 0, goes through 1, 1, and then also 4, 2. So I'll go to 1, 2, 3, 4, 2, and then kind of connect this one. Right. I also need to locate the point 3, 0. That's going to be 1, 2, 3, right on the x-axis here. So we're talking about the shortest distance between this point and this curve. You may think just go straight up to the curve and plug in 3, but actually it looks like you would get a shorter path if you kind of went at it slightly this direction. So we're just going to leave that as like a mystery here. So this distance, I'm going to call lowercase d, and that's what we want to minimize. We want to minimize that distance. Okay. All right, so to do this, this is a really tricky setup. This one is last on the worksheet because it's definitely the most complicated. So I'm going to call this point here, so the point on the curve that's being used as like the representative, we're going to call this the point x, y. The relationship between this x and y would have to satisfy this formula y equals root x because it's on the curve. So whatever x is, y is the square root of that number because we're on that curve. So that makes this distance the distance formula with one point being 3, 0 and the other point being x, y. So I'll do this in steps. It's the distance between x, y, and 3, 0. It doesn't matter which one of these points you consider as like the 1 versus the 2 point here. It'll kind of change the way that the formula looks for a minute, but it all shakes out the same. So I'm going to get square root of x value minus x value squared plus y value minus y value squared. Okay, so you may notice there is a little bit of simplifying we can do. At some point, we'll have to square out x minus 3 squared. But right now, we can at least tell y minus 0 is just y. So all this is just y squared. So our objective function, just like the previous 4, even though this is grosser, the objective function has 2 letters as inputs. And we know that that's kind of like the traditional setup for optimization problems. And there should be some sort of constraint, some extra piece of information that helps us connect x directly to y so that our objective function has only 1 letter as an input. So similar to number 4, it's a lot trickier than the front of the worksheet, but similar to number 4, this formula is the constraint, y equals root x. Because this x, y is on this curve, this must connect those 2 numbers. So I'm going to put root x in for y right here. And then, of course, the square root and the square cancel. I'm also gonna, why don't we FOIL out this x minus 3 squared here? So that would be x squared minus 6x plus 9, and then plus an extra x over here. So that makes this the square root of x squared minus 5x plus 9. I'm just combining this term and this term. All right, so we have both bad news and good news here. So what's good is that we've gotten our objective function to have only a single input, right? So this is the function whose critical numbers we want to find and locate its minimum. The problem, though, is that this function's not great. To find the critical numbers, we would take the derivative of this instead of equal to 0. And while not impossible, it is really hard. It's much more complicated than the previous 4 examples. So in this problem and problems with similar setups that involve the distance formula specifically, we're going to make a command decision that will make the rest of the work more reasonable. So the command decision we're going to make is that the location of this guy's minimum, right? So the smallest output of this formula is going to be the same place where the same formula, but without the root, is minimized. So let me write down what I mean here. So d squared is this formula just without the root, right? Because if you square it, you get rid of the root. So I'm saying the minimum of this function would happen at the same x value as the minimum of this function. It's not going to be the same output value, right? Because that square root is changing your output. But where this is minimized, this is minimized. So we're going to focus on just x squared minus 5x plus 9. So I can call that the d squared function. The square kind of makes things confusing, so I'm just going to switch to a capital D for like a different distance. You could also call it like d sub 2 or just f of x. So once we find the x value that creates the minimum of this, which will just be the vertex of that parabola, we know that we have found the x value that solves this. But if we wanted the actual distance itself, we would have to come back to the formula that has the root in it and use that instead, because that was the actual thing in the setup of the problem. Okay, so we want to find the location of this guy's minimum. We'll find its derivative and set that equal to 0. And we get one critical number, which is 2.5. You could write that as 2.5, 2.5, 5 over 2. It's all the same. Again, when we only get one critical number, it's probably going to be our answer, but we have to check every time, just in case it's a fakey point or it's a maximum instead of a minimum. We want to be really careful. So once again, I'm going to use the first derivative test, and we will make one comment at the end about if you use the second derivative test, what are some of the other options? Because I've used in these video solutions the first derivative test every time. Okay, so let's say we do the first derivative test like we've been doing. I'm going to mark this is capital D prime. Critical number is 2.5, and we'll throw in some test points here. You could restrict this domain a bit, particularly on this side. You could say like there is no x value on this curve after 0, so I could exclude all the negatives. But again, because there's only one critical number, that's not necessary for the problem. So let's say we plug in 1. That'll represent the left-hand side here to my d prime equation. If I plug in 1 here, I get 2 minus 5. That's negative. Something greater than 2.5, let's say 10. If I plug in 10 to 2x minus 5, I get 20 minus 5. That's positive. So d prime is negative to positive, which means d goes down and then up. So we have a minimum here, just like we wanted. Okay, so let's check the actual question. And we're going to be extra careful here because of that command decision we made. Find the point on the curve that's closest. So we want the values of x and y of this point here. And what we have at that 2.5 is the x value. So when x is 2.5, y equals, and we want to backtrack until we have a direct connection from x to y. That's actually the original constraint, y equals root x. So y is whatever the square root of 2.5 is. I don't have a calculator, so I'm going to leave it in that format. So my answer is the point 2.5 comma root 2.5. All right, so let me backtrack for 1 minute and talk about a different way to end the problem. So once we get the critical number 2.5, another option is to use the second derivative test. Let me do this in an alternate color here. So if we did second derivative test instead of this number line stuff at the end, we would start by computing the second derivative of d, which is the derivative of 2x minus 5, which of course is just the number 2. Normally this is a formula that has like x's in it. For this one, it just happens to always output the number 2. So we want to plug in 2.5. We take the second derivative of the critical number. But here there's nowhere to put the 2.5 to compute. So we just say like, okay, well, everybody's output is 2. Because this is positive, the second derivative being positive means d is concave up, which tells us it's making this kind of shape, which actually makes sense when you look back and realize that this was just a parabola that faces upwards. So because it's concave up, that means any critical number must be a minimum value. And we come to the same conclusion here that we did here, just using a different piece of information. The third option, I did start by saying there were 3 options for this step. So first derivative test, second derivative test. The other option is the closed interval method, which doesn't actually work in number 5 because the closed interval method, you have to decide on like a closed interval a to b of reasonable domain. And while the a value can definitely be 0, it's not really obvious where b would be. You could start to make the argument that like points over here are clearly really far away from 3, 0, but it would be tough to kind of make a judgment call about what an appropriate value of b would be. But if you could, like in some of the other problems, and you'll see this in the written solutions, if there is a way to make a reasonable choice of a and b, then you go to the xy chart or xf of x, which for us here would be d of x, and actually plug the endpoints a, b, and your critical number 2.5 into the original function, not derivative, not second derivative. And we would be looking for the smallest y value of them all, which of course should lead us to the exact same conclusion. So we have our 3 options here. And you can see from these video solutions, I default to the first derivative test as much as possible.